Okay, now we're ready for the average value of a function. So, it is defined to be, if you have a function over an interval from a to b, the average value of it can be calculated by taking 1 over b minus a times the integral from a to b of f of x dx. So what does average value mean? Well, let's just take our typical function. Here's some continuous function from, let's say, a to b. Here's a, here's b. Okay. Now, if we take this function and we divide it up into subintervals like we often do. So we're saying, okay, let's divide it up into these subintervals, okay, that are evenly spaced. So imagine that I have spaced these evenly. So we've got this many subintervals. We would take some sample in the middle of one of our subintervals. So we'll pick some value here, x sub I, okay, and then we'll go up and we'll say, well, what is f of x sub I? So this height. So for each of these subintervals, we would go in here and we'd find a x sub I for each of these, right? And let's add up all of the f of x sub I. Okay, we'll add up all of those, and then we'll divide it by the number of subintervals. And what that gives us is the average value, or sort of the average height of this function. This gives the average value of the function. Now, an approximation to the average value of the function. So, as usual, if we take more and more subintervals, more and more, we took, and so these widths are smaller and smaller and smaller, we took more and more, our approximation will get better and better. So, another way to think of this is basically 1 over b minus a is the width of this region. So this is basically 1 divided by the width. And the integral under the curve is the area under the curve. We've learned that. So if we take 1 over the width times the area, or basically if we take the area divided by the width, what does that give us? That gives us the height. Or maybe I'll write it on this side. That gives us the height. So the average value of the curve is basically the average height of the curve. Is the area divided by the width. So that's a way to think of this formula. Now, one of the things that we get as we're looking into this, or that we develop, is the mean value theorem for integrals. So before we look at that, let's recall the mean value theorem for derivatives that you learned in Calc 1. So right here, the mean value theorem for, recall, let's say, the mean value theorem for derivatives. What did that tell us? Okay, well that told us that if we've got some function that is over a closed interval from a to b, that is continuous and differentiable. So some polynomial we'll do for this illustration. So here's some function f, and it's on a closed interval from a to b. Okay, what does this mean? Well, the mean value theorem for derivative said, if you have the situation, then there is guaranteed that you can find some value c in between a and b, that the slope of the secant line from a to b, basically the average slope, you can find the average slope of this somewhere in between a and b. You can find a value c for which you can find the slope of the tangent line there. So what this means is, let's draw the secant line from a to b. Let's do that first. Here's a and here's b. And this looks just almost horizontal, but let's just draw this guy. Well, okay, if it ends up being horizontal, then it's horizontal. That is what it ended up being. So it doesn't matter if it's horizontal or if it's not horizontal. This is the slope of the secant line between a and b. What the mean value theorem says is that we are guaranteed to find at least one value of C somewhere between A and B where this slope is occurring. So right here is another horizontal slope. So this is a value of C, and I can see more than one. This is C1, and here's another one, C2. So to further illustrate this, because what if if it didn't happen to be horizontal, that just happened to be horizontal. What if I go again and it's like, let me choose a different subinterval so that I don't get a horizontal slope. We'll do it again. As long as we have a continuous function on a closed interval, we are guaranteed by the mean value theorem to find some value C in between A and B where the slope of the secant line, we can find the slope of the tangent line equivalent to the slope of the secant line, equivalent to the average slope over A to B. So I have to choose a different B if I want a different slope. So let me choose this to be my B. Okay, we'll say this is A to B. That's still, let me choose a different A. Let's make it more extreme. Let's make this A here so it'll be illustrated a little bit better. All right, let's say this is our A and this is our B. Okay, so for this case, it's still, the qualifications to meet the mean value theorem are still there. We have a continuous function that's differentiable on a closed interval. So this right here would be my secant line in this case between A and B. So if I draw that guy, okay. So that means it didn't quite make it, did it? All right. It just still didn't. So that means that we are guaranteed to find at least one value of C where this curve will have the slope of the tangent line will be equivalent to the slope of the secant line. And so I can see here is one value of C. See how those are parallel? Parallel lines have the same slope. This is a value of C where that meets. So that was the mean value theorem for derivatives. We can find an equivalent slope of the tangent line that's equal to the average slope. That's what that said. Now let's look at it for integrals. The mean value theorem for integrals, what does it say? Okay, it says if a function is continuous on A to B, okay, then there exists a number A somewhere between A and B, a number C somewhere between A and B, similar to this, where we can find the average height, is what it says. So let's look at what that looks like, and let's get an interpretation of that. So on your worksheet, you have it sort of written out, but basically what it says is that this value of C we can guaranteed find. What does that give us? Well, if you take f of C, that gives you the average height. So basically, the mean value theorem for integrals is this function, but we're saying that this is equal to, there's guaranteed we can find some f of C. So let's look at a graphical interpretation to understand what this is saying. This is saying, I'm going to attempt to draw the same curve 3 times. Let's see. It's on your sheet. I'll try to draw it like it's on your sheet. So if we've got some A to B, so here is what I have on your sheet right there. Okay, so we've got some function here. It sort of does this. Okay, it's done trying to make the same curve. So, and let's say this is A. Let's call this A, and let's call this B. And we're going to do it all 3 times. Okay, so this will be our A, and this will be our B. I'll try to pick it about the same place. And this will be our A. Oh, this I got it. I drew it a little bit. I need to do it a little bit. And this will be our A, and this will be our B right there. Okay. So here's, this is X, this is F, this is X, this is our function F, this is X, and this is our function F. Okay, so what does the mean value theorem, the interpretation of it means? Well, before we interpret it, let's just look at this. This is our closed interval, A to B. So underneath the curve, from here to here, from here to here, and this one from A, maybe here to here. Okay, so the same area. So if we chose some value between A and B, let's choose this value here, maybe C, okay? And then we go f of C, what would his height be? If we chose that C, what would the height be? Well, the height here would be here. That would be f of C. So this would be our f of C. And we can see that if we chose that height and we looked at the area under here, it's pretty clear that the area underneath f of C is going to be less than the total area underneath from A to B. The total area under the curve from A to B. So that is one scenario. What if we chose C? This is the first C. Okay. What if we chose C to be maybe right here? Let's choose C to be maybe right here. Okay. If C is right here, and this is f of C, then we'd say the area under the curve for this f of C would be this, and it would be this entire region, right? And it looks very much like the area under this rectangle right here would be greater than the area under the curve between A and B right here. And so what the what the mean value theorem for integrals says is that we're guaranteed to find some value of C where we could pick the height so that if we drew the rectangle underneath that area of that rectangle, it would be equivalent to the area under this curve. So what does that look like? Well, I don't know exactly where it is, but I'm just gonna draw C maybe right. Let me have a look at this guy. Maybe right here. We'll draw the C right here. Right, that means if I went up here between A and B, this would be the area that I'm looking at. I don't think I made it high enough. Let me try again, because it doesn't really look right. I'm going to pick a different C. Okay, maybe I want my C to be more like here. So then the height went here. Oh, is that too high? I think that's too high. No? I can't really make it look right. Maybe I want it to be here. Let's pick it. All right. So then the area under the curve would be here. All right, that's a little better. Okay, what does the mean value theorem say? Well, what part under the curve is not showing up? It's not getting covered under the rectangle. This part. Okay. The mean value theorem, or the the mean value theorem for integrals says that this little area right here is equivalent to this area right here under the rectangle. It sort of fills in so that this area in the rectangle is exactly the area under the curve. There, it's possible to find some value between A and B where that's happening. So there is a little saying underneath the mean value theorem for integrals that says you can always chop off the top of a 2D mountain at a certain height and use it to fill in the valleys so that the mountain becomes completely flat. That's kind of a visual, and it's taken from your textbook on page 462 of what's happening here. And this is a geographical illustration of what is happening with the intermediate value theorem. So now let's do some examples and see how it goes. Okay, example 1 says, find the value C that satisfies the mean value theorem for integrals from the integral is -1 to 2. Find C that, this is example 1, that satisfies the mean value theorem for this integral. Okay. From -1 to 2, 1 plus x squared dx. Okay, so first, if on this closed interval from -1 to 2. Okay, first, it's a good idea to maybe get a sort of a visual of what's happening here. So this is a parabola that's been shifted by up 1. So if we look at this guy, here's a parabola shifted up 1, like this. Okay, this is basically what he looks like. And it's on this interval from -1 to 2. So it's from here to here. So it says there is some value C between -1 and 2 that we could choose where it's at its height of it, the area under that rectangle would be equivalent to the area under this curve right here. So this is the area under the curve. All right, where would we pick that C? So we can calculate it exactly, and we won't be guessing like I was on this one. We're like, oh, is it here? Is it here? Which one looks right? We can know for sure. Because it says that f of C, right, is equal to 1 over b minus a times its integral. Okay, 1 over b minus a is 1 over, what is b in this case? B is 2 in this case, minus, a is negative 1, 2 minus negative 1, the integral from negative 1 to 2 of 1 plus x squared dx. Okay, so let's calculate this because this is what f of c is equal to by the mean value theorem. So this is 1 over 2 plus 1, which is 1/3. And if we go ahead and integrate, this is integral of 1 is x. Integral of x squared is x to the 3rd over 3. And this is going to be evaluated from negative 1 to 2. So this is 1/3 times, evaluate for 2, it's going to be 2. 2 cubed is 8 over 3 minus negative 1. Negative 1 cubed is negative 1 over 3. All right. So then we just add this up. Let's see. This is a negative times a negative. This is going to be a plus 1. This is going to be a plus 1/3 when I distribute the negative. So this is basically 2 minus 1, which is a 1. 8/3 plus 1/3 is 9/3 times 1/3. We get 1/3. Let's see. 9 divided by 3 is 3. 3 plus 1 is 4. So this is 4/3. That's what we get. F of C is equal to 4/3. Now, what do we do with that? Well, we take our 4/3 and then we set it equal to, well, what did I do wrong here? I'm supposed to get a different number. What did I do wrong here? Negative, I missed my negative here. Sorry. Negative 1 plus negative 1/3. This is going to be a positive 1. 2 plus 1 is going to give me 3 plus 3. 3 plus 3 is 6 divided by 3. This is a 6. This is a 2. That's better. So f of C is equal to 2. Now, we are trying to find the value of C. All right, so if f of C is equal to 2, then if f of C is equal to 2, then we write 2 is equal to this function when it's C. So that's equal to 1 plus C squared. So we just solve this for C. So we subtract 1 and get 1 is equal to C squared. Take the square root of both sides. C is equal to plus or minus 1. Turns out we get two values of C where this theorem will be fulfilled. One is at negative 1 and one is at positive 1. Let's see what that might look like. This is a sketch, so it won't be perfect. You could do it on your calculator and see what this looks like. But if you go to 1 or negative 1, basically we get the same height. So what they're saying here is that this area right here would perfectly fill in this area right there. And the area under this rectangle is equivalent to the area under the curve. And what is the average height of this? The average height of this is 2. All right, so that's what the mean value theorem and how to find the average value of a function. This is how it goes. Let's try one more example, and then we'll have a few more. I might do a video break. The second one goes kind of fast, though. It's just, we don't have to find the value of C, so this is not as hard. We just find the average value of the function. So let's do that. The average value of the function is equal to this, 1 over b minus a times the integral. And so you may just want to, go ahead and try this one on your own. And if you can't remember how to integrate, this is going to call for a substitution. Then we'll have a look at that. But here we go. Let's look at, they said find the average value, f of c, either one, this is the average value, for f of t is equal to e raised to the sine of t times the cosine of t dt. All right, so, and it's on this interval from 0 to pi over 2. Is that right? That's right. Okay, so the F average is equal to the integral, 1 over b minus a. So, b minus a is pi over 2 minus 0 times the integral from 0 to pi over 2 of e to the sine t cosine of t dt. This is it. We just got to do this integral. So, this calls for u substitution. Let's let u equal to the sine of t. All right, and then du is equal to the cosine of t dt. So if we rewrite our integral in terms of u, we need a e to the sine of t, which is e to the u. And then we need a dt. Well, cosine dt. And cosine dt will be achieved simply by writing down du. So that worked out really nicely. We still have this 1 over pi over 2, and 1 over pi over 2 is the same thing as 2 over pi. Let's adjust our limits for u. We can do that easily. 0, put that in for t. The sine of 0 is 0. Pi over 2, the sine of pi over 2 is 1. And so we've adjusted our limits. Let's integrate. E to the u's integral is e to the u. Let's evaluate it from 0 to 1 times 2 over pi. All right? This is 2 over pi e to the 1. E to the 0 is a 1, minus e to 0 minus 1. And so this is the average value of this function from 0 to pi over 2. Okay, I'm going to take a pause and we'll do the last few examples on the second video.